Hello, welcome back to the 10 Days of AI Basics with Harper Carroll. This is Harper Carroll AI, and today we are on day 3 talking about model architecture. I'm really excited about this one. It provides a lot of insights into how models work. We have a lot to talk about, so let's just get started. So model architecture is the backbone of machine learning models, and it talks about the structural design of the model and how the internal components relate to each other. And so what we have when we have a machine learning model is we have the data, which we talked about on day 2, and you should go back and watch that if you have not, and also watch day 1. And the data plus the model architecture combines, the data flows through this raw model architecture to create our trained model, which then can do things. And we will talk about training, model training on day 4. But for now, we're talking about the architecture, the raw structure of the house of the model. It's the raw backbone of the house. It's kind of like the blueprint of the house. And then we have to fill it in with the actual pieces that we have in the wallpaper and all that, which would be kind of the data. But anyway, so a well-designed architecture is crucial for a model's performance and accuracy and efficiency. And it dictates how effectively a model can capture the relationships and structures within the data. So, if you have a more complex model with many layers, which we will soon talk about, you might be able to capture more relationships between the data, but you also might have the model be too specialized on the data set that it's received so that it actually doesn't generalize well, which means when it receives new data, it's been so focused on the data that it's seen that it actually doesn't perform well on new data. So there are these trade-offs, which we will talk about. And the choice of architecture also significantly impacts computational demands. So a more complex architecture might be more accurate, although it might produce overfitting, which is what we just talked about, where it's really, really trained on the training data and actually doesn't generalize to unseen data well. And it also might require more processing power in the sense that if you want more layers, which we will soon talk about, you will have to update the parameters for each of them, which will take a lot of computational power. So this is just a brief overview. We'll get into what all these things mean. Data, if you recall, we talked about it on day 2, data pre-processing and feature extraction. If you haven't seen day 2, watch that. This covers that. So one of the main architectures that we see in machine learning are neural networks. Neural networks are the foundation of deep learning. So when you hear deep learning, that refers to neural networks. And they're composed of interconnected layers that perform computations on input data to extract these meaningful patterns and then make predictions from those meaningful patterns. These hidden layers play a crucial role in the network's learning process as they transform the data and enable the network to learn these complex relationships. So what we mean is something like this, and I'll go back, but we have these layers, these hidden layers, this input layer, and we have this output layer. So let's go back. So the components of the neural network are layers, which is what we talked about. It's built upon these layers, which are the input layer, the hidden layers, and the output layer. The input layer is where the data comes in, which is formatted as a vector, which is a string array of numbers. That is the input layer. That is the data represented as numbers. Then it goes through these hidden layers where processes are done on them, and we can't really see it. This is where the black box occurs. This is like the model kind of uses these hidden layers and updates the numbers in the hidden layers to learn complex relationships between the input data and the expected output. And so then they kind of assemble all these functions in these hidden layers to properly transform the input into the output. And that middle part, that's the black box. We don't really understand how the model makes these functions that transform it, like what the functions mean, what features it's understanding from the input that then can translate into the output. But there have been a lot of new exciting studies and research output by companies like Anthropic and OpenAI that have helped with model, as they say, interpretability, which means we are starting to understand what's happening in these neurons in the layers. And so neurons, we'll move on to the next part, they are the little nodes. The neurons are in each layer. They're interconnected units, and they pass data forward through the model and then back as the model is learning. So when you're training a model, not only is data passed forward through the model, so from the input to the output, but you're also passing data back as the model is seeing how it did. It's evaluating, okay, this was the output I got, but this is what I should have gotten. It's calculating a kind of loss, which we will get to in the upcoming days. And then it is updating its parameters in the hidden layers to then next time data comes through, it ideally will perform better. So it will have a closer, more accurate output to the true labeled output. This is a lot. I know this is a lot. So please leave your questions below. Maybe type them up now. And then if I address them going forward, you can delete them. And then any remaining ones, leave in the comment section. So we have these neurons, and they kind of look like this. So they're the little circles here. These are neurons, and see how they're interconnected. And the layers are made up of neurons. The input layer, this is our data represented as an array. So this is just like an array, number 1, 2, 3. This dimensionality of this array is 4. The dimensionality of this layer is 5, 5, and then 4. So again, different connection types like fully connected or convolutional determine how information flows between the layers, and we will get to that in today's talk. And we also have activation functions as part of this model architecture. They introduce non-linearity into the model. So if we had very simple data, we could just, for example, like a simple regression where we have house size, house square feet mapped to the cost of the house in a certain area of one location. We might see that it tends to go up and to the right. So as house size increases in this one area, price also increases, and it tends to be kind of linear. We don't need anything special for that. I can't tell if this is flipped, but non-linearity would be if it's not just straight up and to the right or down and to the right. It might be a bit of a curve. That's non-linearity. So activation functions help introduce the non-linearity into the model so we can learn these complex patterns. We will talk about those as well. So the input layer, it has the raw features, the input data. Sometimes we know what those features are. So in the case of like structured data, which is we talked about before, right, where we had this represents height and this represents weight and this represents blood pressure. Or we could have unstructured data where this is just an array of elements of an image. Like we just transformed the image directly into numbers that's then put in as the input. Or it's text, a series of tokens. Tokens are the numbers representing fragments of words or full words. Then we have the hidden layer. This is processing the input data and generates output to be passed into the next layer. So it applies a set of weights and biases to the input data and performs various calculations using these activation functions. And then we have this output layer, which produces the final output or the predictions based on everything that happened in the hidden layers. So we will go through that now. So let's actually just quickly do an example. Imagine a neural network designed for classifying images of cats and dogs. The input layer would receive the raw pixels of the image. The hidden layers would then process this information, extracting features like edges, shapes, textures, and then finally the output layer would produce the probability of the image being a cat or a dog. So then it would be like, it would have 2 nodes here, and this would be the probability of cat, and this would be the probability of dog, and then it would choose the higher one as the final classification. Okay, so let's talk a little bit more about the input layer. The input layer is the starting point of a neural network, so it receives the raw data, and the dimensionality, as I said, is the number of features or attributes. So it's, the number of features, or it's just the length of the vector coming in. It determines the number of neurons. So dimensionality is the number of neurons in the layers. So the input layer will shape the input into a format that is compatible to then be processed in subsequent layers. So it might resize the data or flatten it. Basically, it just makes it fit into the rest of the flow of the model architecture. So for example, here we say an image data might be reshaped into a one-dimensional vector. So whereas you might have like a square image, you would flatten it into one string of numbers, one long, like string, I shouldn't use that word because it represents something else in coding, but it's one long array, one-dimensional array. Again, higher dimensionality means more neurons are needed to represent all the input features. And if you have a higher dimensionality, that means you'll need more compute. But it also can capture more complex relationships and more fine-tuned features, if that makes sense, right? It's like the more high def an image is, it has more pixels, but it also takes more compute to have that high def image. So we're going to go through a bunch of different types of layers. And first we'll talk about a convolutional layer, which tend to be used in convolutional neural networks, which are used primarily for images and video. They apply a convolutional operation to the input data, which involves a sliding filter or kernel across the input volume.
So as the kernel, which is in the middle, is sliding over the input on the left, it's producing the output on the right. And as it slides over, it multiplies the item in the kernel with the input value directly below it, so the one it's directly on top of, and then it adds all of those multiplication products together. The stride is how much you move the kernel at each step, and this stride here is 1 because it's just moving 1 to the right and then 1 down as it goes to the next line, to the next row. So in this section, it's 0 times 0 plus 0 times -1 plus 0 times 0 plus 0 times -1 plus 60 times 5 plus 113 times -1 plus 0 times 0 plus 73 times -1 plus 121 times 0. And so we get 114 if you add that all up.
So we saw the filter, which are the little matrices that we slide over the input. The stride is how much you take a step with that filter as you move it. The padding is what we put on the outside of the matrix, of the main input matrix. The feature detection is this combination of filter size and stride and padding, and then it ends up saying what types of features that the layer detects. So smaller filters will capture more fine details, right? Because if you have a smaller filter, you won't be reducing large chunks into like one, right? Because each filter, you just get one from it. So if you have larger ones, you're kind of reducing the size more. If you have smaller ones, you're reducing it less. So it has finer details, and larger filters focus on broader patterns. And you might have multiple convolutional layers. So some are larger, some are smaller, and the model kind of learns different aspects of an image. So in some layers might learn more fine-tuned details about, an eye, while the larger filter might learn, generic edges or shadows or things like that. I don't know, I'm just making this up. Then we have a pooling layer, which is known as a subsampling or downsampling layers, which also tends to be used in convolutional neural networks, as in for images, because they're really good with spatial data. So data that has to do with like geography or coordinates or, the placement of images of things in a location. So location-based things. So that obviously works well with images. So what pooling does is it decreases the number of parameters and therefore the computational complexity in the network, which also reduces overfitting, which is what we talked about before. As you have decreased number of parameters, there is a decreased chance for overfitting, which is when you learn the training data too well that you don't perform well on new test data because you've fit so well to the training data. And I showed an image of this in day 2. So if you have outstanding questions about overfitting, please leave a comment, but hopefully the description in day 2 was clear and the associated graph in day 2 was clear. So what pooling layers do is they summarize the information within local regions of the input using a specific pooling operation. So we have max pooling, average pooling, and it helps with learning features that are invariant to minor variations in scale and orientation. So like if you were to change the orientation, it kind of just, again, increases the generalization of this model and just makes it a little bit more like broad, less fine-tuned, less high dimensional, high def. And so max pooling is when you have this filter kind of, it's like when you look at, you have this block and you're looking at a bunch of neurons and you choose just the maximum number there and then you reduce it down to that. So I'll show images here. So we have max pooling and average pooling are two main types of pooling to reduce dimensionality in usually just convolutional neural networks. This should say physical, not -physical, by the way. I must have had a weird typo there. Now, another type of hidden layer are recurrent layers, and these tend to work with sequential data, such as time series data, or text sequences, like sentences. So RNNs, unlike feed forward, which only goes forward, never looks back, RNNs have the ability to remember past information, making them good for capturing temporal dependencies in the input. So they're able to kind of like understand sequences and look far back. And, you know, in a text, say, if you were to say, John and I went to the park, we had a good time. We, because you have this temporal understanding, you know, refers to John and I. So you kind of need this like memory. And so RNNs are specifically designed for processing sequential data to remember past information. LSTMs are more advanced forms of RNNs, and it's a more advanced architecture, recurrent architecture, that helps address vanishing gradients. So gradients are when you're updating the model's parameters, and it kind of tells the parameters how much to change. But as you go further and further back, you're multiplying the gradient so you go forward through the network, you get the gradient, and then you go back, you send the gradient back. And at each layer, as it goes back and updates the parameters, it's being multiplied. And eventually, if the number is less than 1, it gets smaller and smaller and smaller until it's so small, there are basically no updates. And that's a vanishing gradient problem. And so LSTMs and GRUs help address this issue. I don't want to go too in depth onto how these work in this lecture today because these are like their own video. And this is already quite a long video and we have a lot more to do. But just know that recurrent layers are good for sequential data, they're good for remembering, and these are 3 different forms. LSTMs and GRUs are more advanced forms. And yeah, exciting. Dropout layers are also a method to prevent overfitting. And it works by randomly selecting a fraction of neurons to just drop out, so set them to 0. So these are like layers where you just drop out neurons.
So you set a dropout probability, and then at that layer, every neuron has a chance of dropping out, i.e. becoming 0, at that probability.
So this forces a network to not become too reliant on any single neuron or set of neurons. And so it tends to distribute the features across the neurons. It kind of prevents just relying too heavily on a small set, in which case it's like, what's the point of having so many neurons? We should actually use them because it's computationally expensive to have all these neurons. So we need to make sure that we actually distribute our understanding across the neurons. And so this helps the network learn more generalizable features, meaning that it can learn features that generalize to new data by forcing it to adapt to subsets of features. So it really has to learn better. For example, if you had a model where you were classifying a cat and it had this feature meow, and the meow was so strongly coordinated with it being a cat that the model just didn't really use any of its neurons, and it just so heavily relied on the neuron that said, is it meowing or not? If you were to remove the meow, the model wouldn't know what to do. It would perform terribly because it's relied so heavily on this one feature. And so then you're forcing it to say, okay, if that meowing is gone, what else can I use to see if it's a cat? Does it have sharp, pointy ears? Does it have a long tail? How does it move? What are the paws like? Like, it has to look at a greater variety of things than just like a one strong super indicator. Batch norm normalizes the inputs of the layer, which helps with training speed and performance and stability. And so you're basically setting the numbers into a certain range that helps the model kind of like if you can imagine it like this, if you were playing with balls and you were like grabbing them and you had to like jump over here and over here and over here and do these like complex things. But what if you were to just like reduce the scope of where the balls could come in? It involved a lot less effort to grab all the balls. So normalization, I don't know why I came up with that example, maybe because I'm in a circle right now, but it's kind of like that. Like it shifts data that can be like so far skewed to just kind of like in a really workable way. So it reduces the computational intensity of a lot of the tasks that the model needs to do. We have a fully connected layer, which are also known as dense layers, and those tend to appear in the final stages of deep learning architecture. So they are like right before the output or are the output. And so in the fully connected layer, each neuron receives input from everything in the previous layer. So all the neurons in the previous layer, everything is fully connected, like in this image. Let's go all the way back. See, this is fully connected. So every neuron is fully connected to everyone before it. So these are all fully connected layers. So they are able to create a representation that is suitable for this final classification. They're able to look at all of the learned features and how everything connects with each other, so that it's kind of just like this last hurrah of like, what have I learned? How does everything connect to each other? Let's all like grab it all together, and then we can transform it into this output, into the classification or regression. We will get into what those words mean. Then the output layer tends to be the softmax layer, which is responsible for converting the raw outputs of the network, the logits, so logits are just the raw outputs of the network, and outputs of probability distribution. So make sure that it transforms just these raw numbers into like numbers that all sum to 1.
Here's an example I found online, classifying an MRI into brain tumor classification. And it takes the logits on the left, passes them through the softmax function, and then outputs probabilities for the various classes because they all sum to 1.
So all of the classes will add to 1 after it goes through the softmax layer. And the probability reflects the network's confidence in each class. So what you tend to do is then just take the class with the highest probability, and this is for a classification task. So softmax tends to be used in multi-class classification problems. In that, like, for example, are you assigning an image to be a cat or a dog or a duck or whatever. That's a classification problem. You have an image and you're putting it into a set number of classes, cat, dog, duck, and Softmax is good for that because you have this probability of likelihood for each class summing to 1. So you just take the one that has the highest probability.
I just wanted to quickly go over one activation function, ReLU. So remember we talked about how it adds nonlinearities to fit more complex data. What ReLU does, it's one choice, and it basically sets it to 0 if the input is negative and just keeps it the same if it is not. And so here is one example.
Okay, so we've gone through the layers of a neural network, and now we're going to talk about architectures for different types of machine learning. So remember we talked about in days 1 and 2, we talked about supervised learning, we talked about unsupervised learning, and we talked about reinforcement learning. So let's just quickly recap those, and we'll talk about the different architectures that tend to be used for those different types of models. So supervised learning, again, as a quick recap, involves training models on labeled data where both the input and the desired output are provided. So it's kind of like having the answer is right there and you're learning, I have a picture and then I know this is a cat. I have another picture. I know this is a dog. Another picture. This is a cat. And so you're able to see these examples and then look at a new picture and say, is this a cat? Is this a dog? Is this a duck? Based on everything that I've seen before about what I think makes up a cat, a dog, and a duck, based on the data, the labeled data that I saw before. So common tasks include classification, which is like I just described, regression, which is when you're basically trying to take a set number of features and output like a number. So for example, we're saying, house prices is a common regression task where we have these features, number of rooms, size, square feet, location, age, and then the label, which is the price. That's the regression task, is to you output this continuous price, meaning it could be just any number. It's not like a set number. It's not discrete. It's not a set number of classes, which would be cat, dog, duck. That's discrete. There's 3. Whereas it's continuous. It could be like any number, really, like above 0. And object detection, which is looking at an image and saying, inside this image right here is the green light, or inside this image, there's a car here and there's a person here. So for these types of supervised learning tasks, we have decision trees are often used. Those are simple and yet powerful models that are actually, people say they're not useful, but they actually are useful. I see them used quite often. And one of the really great benefits of decision trees are that they're interpretable. And we'll go over how they're interpretable, but remember, interpretability means that you kind of know what decisions are important for the model to determine the output. So with neural networks, we have this infamous black box where we don't really know what features the model is using to create an output. But decision trees you actually do know, and I'll show you that in the next slide. Neural networks we just talked about. They are more complex. They involve a lot more computational intensity because you're updating all these parameters, doing backpropagation, and CNNs, convolutional neural networks, which are a type of neural network, which we talked about with images, and they use convolutional layers. So for decision trees, they have this tree-like structure. So let's give you an example of whether to play tennis. So the features inputted are weather, temperatures, humidity, wind, and we want to decide whether we want to play tennis. So it starts sunny, overcast, rain. If it's sunny, then we go to this next thing. How humid is it? Is it high humidity? Then we don't want to. Is it normal? Then yeah, let's play. Is it overcast? Yes, perfect to play. Is it raining? Yes, okay, it's raining. So is it windy? If it's strong winds, let's not play. If it's weak, we can play. And so we have this root node, the weather, and it branches. And so you're actually able to learn based on what kind of decision tree you use, but there are lots of different types of decision trees that you can use, but you can actually learn which features are most important. So this is really basic, but like I trained a model when I was for my graduate degree that was predicting the probability of successful vaginal birth after a cesarean section, which my friend's in medical school, so I did it with her. I didn't know this, but apparently after you've had a C-section, you might not ever want to have a vaginal birth. I don't know. Apparently it's a thing. And we have these features, which are like age of the woman and, health background and situation with the baby. And you're able to actually train a decision tree. And there are methods to do this where you don't have to like manually go in, but you pass in these features and then the decision tree forms itself. And then you can go back in and say like, which features are actually most important for determining whether someone will be able to have a successful vaginal birth after cesarean. So, is it the position of the baby? Is it, the age of the woman? Like you can actually figure out the features. So it's interpretable in that sense. It's really cool. Okay, another type. This is a feed-forward neural network. We talked about neural networks. Feed-forward networks are when we don't go back. Remember we talked about recurrent neural networks where we do go back. Feed-forward is it's just everything moves straight. And a multi-layer perceptron is a feed-forward network with at least one hidden layer. So we talked about hidden layers. Sometimes you may not need a hidden layer if you have like a really simple regression task. You can basically just like do one operation on the input and have an output. So like logistic regression is just a really simple feed-forward neural network. And I'll show some images of that. So here we have the input layer. This is the bias, etc. Convolutional neural network, I'll put an image up here.
So here we have the input, image, and we have the kernel, which we talked about, convolutions, ReLU, which is the activation function, which we also talked about, the flattening layer, the fully connected layer, and the output. So you might recognize these layers, and then it classifies it and goes through Softmax.
Unsupervised learning can be unsupervised learning where you have the labels. Unsupervised learning is when you do not have labels. And we talked about this in the context of like clustering and finding like things and throwing words on a wall and seeing how they relate to each other. So we have these unsupervised learning where you're not really learning labels for things, but you're just kind of looking at the data and able to change the data, alter the data, see how it relates to each other, find structures. You're kind of just like looking at it. It's about discovering patterns and structures. It doesn't have explicit instructions. And this is a good example. It's like exploring a city without a map. So you're just looking at observations and patterns, and you're not like, this area is Times Square. You're like, oh, like, this is kind of cool. This is more dense. There are a lot of people here. And then you could have like a map of the city with like density and things like that, where there are no explicit instructions or labels. You're just kind of understanding the data. Autoencoders are neural networks trained to reconstruct their input data. And what they're mainly used for is what they basically do is they reconstruct their input data. So they're kind of learning to compress the data.
Autoencoders compress the data and then reconstruct it back to its original form. And so this process of compressing it, naturally they learn a lower dimensional version of the data.
So this is really good for like dimensionality reduction. Obviously, feature learning, so it finds which features are the most important. So if it has to strip away features, it doesn't want to strip away the most important ones. It wants to strip away the ones that will not change the output the most. So for example, in the cat example, we had the feature of meowing, eyes, ears, tail. You definitely wouldn't want to get rid of the meowing feature because we knew that was super important. But maybe we want to get rid of maybe the shape of the nail isn't very important. Or maybe the skin color under the fur isn't very important. We can just throw that out and we can reconstruct the data really similarly. Generative adversarial networks involve, they're adversarial, so it's two competing networks, a generator, which creates new data samples, and discriminator, which tries to say, is that real or is that fake? So for example, say you want to create images in the style of Van Gogh. And so you train this generator to look at Van Gogh and then make a new image that isn't Van Gogh. And then the discriminator has to look at the image that the generative adversarial network sends it and say, is that really Van Gogh or is that just one made by the generator? Both models have loss functions. The generator gets the feedback, did I properly fool the discriminator, in which case it's doing well, or did I not, in which case I need to do better. I need to update my model parameters to make my next creation better, more able to fool the discriminator. And this discriminator has its own loss function. It says, did I guess correctly whether it was a fake or not? If I was fooled, then I need to do better. I need to update my own parameters to better tell whether it is fake or real. And so you have these two networks, and this is how deep fakes are made. So deep fakes are these videos that you see that aren't real, but they really look real. Very cool. I want to make a whole video on GANs because they're super cool. Okay, and now we're going on to reinforcement learning. Reinforcement learning centers on agents doing trial and error. So you make sequences of decisions and environments and you get feedback. So it could be positive, it could be negative, it could be neutral. And then you learn how to navigate the environment. So like learning to ride a bike, or, I like to give the example of a child in the state where it has a hot stove in front of them. Perhaps it has already tried turning and walking away from the stove, in which case it's gotten no reward, it's 0, the reward is 0. Or it could try touching the stove, in which case it would get a reward of -10. So then in the future it knows not to touch the stove. However, reinforcement learning also has the concept of time. So it wants to maximize its reward over time. So for example, you might take on a heavy debt to go into college. So, right away, it seems like it's negative because you haven't earned anything in school yet, and you're down however many thousands of dollars you had to pay to go to school. But you think that over time, the reward will be positive. It will offset the negative, and it will be so far positive that it was worth it. It was worth this initial negative. So it has this concept of time, of looking far ahead into the future. Q learning learns a policy by estimating the value of taking an action in a given state. So I'll go into both of these different types of reinforcement learning methods, Q learning and policy networks. So Q learning is a value-based method and policy networks are a policy-based method. So we'll talk about that now. So Q learning is a value-based method which focuses on learning the value of actions and driving a policy from these values. And so a policy is your own internal policy of, given a certain state and given all the actions available to me from this state, and considering all future actions into infinity, what action should I take in order to have the highest future expected return? So knowing that I get rewards or penalties at every step, and knowing that I'm going to go off into infinity, which action should I take right now from the state I'm in right now? And states have different aspects to them. So, I am in this room. I'm currently in one room of my house. And so there are a certain subset of actions available to me. I can't walk through, I can't go left because then I would walk through a wall, but I can go right. And then if I go into the next room, then I could go left. And your state represents the current environment that you're in, and your actions are based on the state, and you want to consider everything into the future. So again, Q-learning involves learning a Q value function, which is estimating the expected cumulative reward for taking action A in state S. It updates its Q values using the Bellman equation. And I will put this Q equation on here so that we can learn what is Q. Let's go through the function together.
So Q is an estimate of the state action value function. And so again, it takes in the state and action, and it estimates the discounted return over time. And so we have this discount value, gamma. We also have a learning rate, which, if it is a constant, it will decrease past values. And so we have these basically two discount values where gamma is for future. So this is the future estimation over time. So if you take the action that maximizes this Q function, so this is estimating in the future, and as you go further into the future, this gamma value increases. So it iteratively increases as you go further into the future. And then this is, the current and the past. And if we change this alpha value, this will reduce past values. And then this is the next state. This is temporal difference learning, where the increase is proportional to the difference between the present and past estimates.
There's also the concept of exploration versus exploitation, which we have in reinforcement learning, where the agent will explore randomly with a probability epsilon, or it will exploit, which the term, when used in the context of reinforcement learning, means that it's using what it knows to be the best action given its history. So if you're in a city that you've been in before, you could explore, you could try a new place that you haven't tried before with the potential of not liking it, or the potential of liking it more than the place that you like the best. Or you could exploit, which is just going back to the place that you know you like the best and getting that set reward, that reward you know you're going to get from your highest rated place. I want to also do a video on Q-learning. If you might have heard of Q star from OpenAI, I believe that refers to the optimal Q in a Q-learning algorithm.
Q star, or Q asterisk, is the optimal Q, and it is possible when you are able to sample from all possible outcomes forever over time.
Policy-based methods directly learn the policy mapping states to actions. So given the state, you go to this action. So it's good for high dimensional or continuous spaces, but it requires more data and computational resources. So they map states to a probability distribution over actions, whereas Q-learning you store a state and then you do the best action pair. So it's state and then one action, or explore. But here you have a probability distribution over all the actions. So that inherently encompasses exploration versus exploitation, because it's a probability distribution. So there's some stochasticity, which I talk about in my Instagram video, and I will link that in the bio below. And again, this is something that I want to go more in depth into in another video, because this is quite a long video at this point. But these are the types of architectures for different types of reinforcement learning methods. So now we get to our conclusion. Model architectures share some fundamental components, like many have layers and neurons and activation functions, but the way that they're arranged and the types of layers that they use do vary significantly. And so the architecture that you use really does depend on your task and the complexity of the data that you're using. So yeah, I hope that this is helpful and that you understand architecture a lot better. In terms of choosing the right architecture, it is this balance, right, of the data set size and the complexity, but then also the available computational resources. Training a neural network takes quite a bit of computational resources. It depends on, where you start from. If you have a model that exists already that does a task quite similar to the task that you'd like your model to do, you can start with a major head start in fine-tuning the parameters of the model or training the parameters of the model. If there is a model that exists that does tasks similar to what you are trying to do, you could start from that model and drastically reduce the amount of computational resources that you need. For example, if you have a model that can already classify different types of cats and you want to just add even more fine-tuned types of cats, you could start from that model because it already is looking at features that differentiate types of cats. And so that would be better than just starting with a model that just randomly chooses outputs at the beginning, like the weights are totally random or uninitialized, or even like when you're training a model from scratch, which is not really done as far as I know much these days. Maybe it is if you have like a lot of amazing resources, but you start with basically random values in the hidden layers, and then you do so much training on the data that you're able to converge. And starting from random is really different than starting from a model that's already learned a lot and has values that have already been fine-tuned, updated to represent the data that it's trying to encapsulate. Like it's trying to take this input and transform it into the appropriate output. So if you have a model that's already done a lot of that work for you, you can start from there. That's called transfer learning. So yeah, you want to look at the problem type, the dataset characteristics, the computational resources, see if there's another model that is similar to what you want to do. Maybe just use that model. So I hope that this was helpful. I hope that this helped you understand model architecture a lot more. And if you have any outstanding questions, I hope you were writing them down as we said, and then you deleted the ones that you don't have anymore. If you have outstanding questions, leave them in the comments below. Let me know what else you want to learn. Let me know if this was helpful. And I hope to do more coding tutorials and things like that. I saw that many of you liked the Llama tutorial that we did last week. And if you want to do more things like that, let me know. If you have specific suggestions on guides you want to do, let me know in the comments. And I hope that this is helpful. If you liked it, please like and subscribe. It does help me a lot. And yeah, I really like doing this with you. It's been so great to connect with you. I'm hoping that these are helpful. So let me know in the comments. And I hope to see you back here next week. Tuesday, we have another AI news update. And Friday, we will have another more in-depth learning together. And if you haven't subscribed to my Instagram, check that out. That is at HarperCarrollAI. So please share with your friends, like, subscribe, and I want to connect with you. So let me know your questions and suggestions in the comments. Take care, everyone. See you next time. Bye.